for people to fully appreciate the power of quantum computers and to accelerate their use in different fields, people should be learning the fundamentals of quantum, even at a young age.
This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Potker. At the quantum scales of molecules, atoms, and electrons, the laws of physics become peculiar. NSF-supported researchers are exploring how to control the behavior of these quantum systems to translate quantum knowledge into next-generation technologies such as quantum computers that can tackle complex problems that are beyond the capabilities of even the most powerful supercomputers of today. We're joined today by Christopher Monroe, Gilhooly Family Presidential Distinguished Professor of Electrical and Computer Engineering and Physics at Duke University, and co-founder of IonQ, the first publicly traded quantum computing company. Professor Monroe, thank you so much for joining me today.
It's a pleasure to be here.
I want to start with a general question. People kind of get lost a little bit, maybe glaze over when you mention the term quantum computing. What is quantum computing?
The question. Well, let me start with maybe the bad news. In quantum computing, we don't yet know exactly how these devices will be used in the future. The very good news, and to me, it's not hype, it's the fact. Quantum computers are able to process and store data in ways that are impossible using standard computing machinery. And that's why they hold great promise for mostly unknown applications in the future. And so they're based on, and the reason I can say all this is that they're based on totally new physics, really physics that is not part of our everyday existence. There's no explaining certain things using everyday intuition. So this is interesting, and the downside to that is that people aren't used to them. There's some very weird ideas behind it, and some people don't even believe in it. I think we're maybe fortunately beyond that second statement that people are starting to understand that I'm sure we'll talk about the industrial play in quantum these days. It's largely driving the field now. It's a very interesting time. But if I had to go to 101 quantum computing, I would say the bits that we're used to in classical computing, zeros or ones, they are called quantum bits. That's one way to process quantum information. Quantum bits can be in a superposition of 0 and 1 at the same time. And when you add more and more bits together, the configurations, the possibilities grow exponentially. And that's really that's the bonus. We can store exponential amounts of information, way more, even with hundreds or thousands of bits, that's way more information than we could store in classical machines. So it's very sci-fi-like in a way. There's a lot of hype behind it. We know they're going to be useful for something in the future. The question is when. It's a wonderful confluence of fundamental physics and very applied engineering and real devices of the future.
In your devices, you're using a trapped ion approach. Can you talk a little bit about what that difference is?
One of the chief and most difficult requirements in a quantum computer is that you can maintain a superposition of states. You can have a 0 and 1 at the same time. And the trick is, the way I think about it is, these superpositions only exist as long as you're not looking, as long as it's not observed. So you demand an extreme level of isolation of these systems to do the computation. The computation happens without looking, and that's very tricky to do. It's hard to control something when you can't even look at it. So we indeed use individual atoms as the bits. There are many flavors. They don't have to be atomic ions. They don't have to be charged atoms as we use. They can be neutral atoms, they can be single electrons, single photons, but they should be something quantum, something that obeys these strange laws of existing in superposition. The trapped ion approach, these are individual atoms that are charged, and because they're charged, we can control them so well. We can apply electric fields and actually we can levitate them with electromagnetic fields, and they're in a vacuum chamber because not only can nobody look at the system can't be disturbed by the environment, for instance, by air. So we get rid of all the air, they're in a vacuum chamber, and they're floating. They're not part of a surface. They're not part of a solid. They're just sitting there all by themselves. They see each other. And so this is, trapped ions are acknowledged to be sort of the purest form of isolation of qubits. And there are lots of engineering challenges to scale this platform up. But yes, individual atoms, these are sort of like the transistors of our quantum computers.
I want to build towards where you are today a little bit and ask you about your earlier work. How did your early work with featured Nobel laureates, you were working with laser-cooled atoms and entangled atoms, how did this set you on the path for working with quantum computing?
I worked for many years in Boulder, Colorado, with David Wineland at the National Institute of Standards and Technology. We were basically the atomic clock division of the U.S. government. But more than that, we weren't really making primary frequency standards. We were conducting research on to make them better and what the future clock pieces would look like. And we, in fact, figured out that by entangling, this is a buzzword I'll explain in a minute, by entangling multiple atoms, we could make the clock run with better signal to noise. So this is largely academic at the time because the improvement was marginal. If you entangled two atoms, you had a factor of two, roughly two better in signal to noise, which is, factor two is nice, but it's a lot of work to entangle them. So we were playing around with the physics of entanglement, being able to do all kinds of foundational aspects of studying the entangled superposition. So an entangled superposition is one that has more than one qubit. And the reason it's weird, this is first pointed out by Einstein in the 1930s. He thought he had a way to prove that quantum mechanics was wrong, and he came up with an example, and it's called entanglement. Now, if I give you two qubits, I think of them as coins sometimes, heads and tails, zeros and ones, whatever you want. If I produce two qubits and they're in a superposition of both 0 and both 1. That's a very interesting superposition because when you measure just one of those two qubits, what happens is and I didn't say this earlier, it's important, you have to look at qubits in the end. I mean, what good is a computer that you never look at? So when you measure a superposition, it randomly pops into one of its many states. So there's sort of noise coming out of the ether in a way. This superposition that's entangled, I mentioned 0, 0 and 1, 1. When you look at just one of the two qubits, you know its state, you measure its state, 0 or 1, but then the other one gets measured also implicitly at the same time because they're correlated. You prepared them in this entangled superposition. And what Einstein realized is that that's very strange because it appears that there was action at a distance. These qubits could have been really far apart, and by measuring one of them, somehow we learn that the other one is in the same state. And that's very strange. It doesn't violate any laws of physics, of course. It doesn't allow you to communicate information faster than light, because even though you know that state of the other qubit faster than light could have made the distance, if you do it over and over again, it's totally random, and there's no information content in random bits. That's sort of the close of that paradox, but Einstein didn't know about information theory at the time in the 30s, I guess. So we were making entangled states for these clocks for academic reasons, just to, and indeed to do foundational quantum studies. And then this is 1993, 1994. And then Peter Shor published his algorithm that showed that if we had a quantum computer, we could factor numbers into their primes. We could therefore break codes, break public key encryption systems. And this was a big deal because it seems to have changed the complexity class of a certain problem. In other words, it put quantum computing on the map. It showed that, yes, there is an application. It's not, as I said earlier, we don't know what it's going to be used for. We do know there's one exception. We know it will be used to factor numbers, which sounds kind of boring in a way, but it's very important for cryptography. So we sort of backed into the field of quantum computing by making clocks. And, I guess I lived through that, and I'd been told that you do basic research, fundamental research, you never know where it's going to go. And most of the time it fails. It doesn't go into a cool direction. But this is one example. It's kind of a spectacular one where studying one thing pivots into something else. And, that was 30 years ago. And it's been a remarkable growth since then. So early on, playing around with these atoms to make better clocks. And this followed upon my work going toward Bose condensation with cold atoms in Carl Wyman's group, also in Boulder, that gave me the background in atomic physics to start this path of quantum computing.
As you said, it's been a number of years since then and things have progressed. At what point did you know it was time to start a company?
I suppose it was when a particular venture capitalist visited my office and said, it's time to start a company. I certainly wasn't going to go out and I didn't know how to start a company. I wasn't going to go out and try unless the bar was low and there was a good business plan. And it wasn't that simple, but there was a particular venture capitalist, really nice guy, named Harry Weller. He visited my office in College Park, Maryland, 2014, so a little more than 10 years ago. And he had a physics undergrad degree, so he could read some of this stuff. And my colleague and friend, Jungsang Kim, so I was at Maryland at the time, and Jungsang Kim at Duke, we started collaborating about 10 years before that, building bigger ion traps, thinking about how to scale up, applying lots of engineering approaches, making it cheaper, using lasers that were much easier to use. And so it wasn't a business exactly, but we were sort of plotting the path so we didn't have to worry about all the atomic physics and the control of atoms with optics. We could start thinking about programming small algorithms in our machines. And we were actually doing that. And this, we wrote a paper, it was an architecture paper, how to scale a large scale quantum computer based on photonic interconnects and so forth with these trapped ions, although it's more general than that. And this venture capitalist apparently read PhysRev A, Physical Review A. He read that paper and he waved it in my face in my office. He said, this reads like a business plan. And so I sort of laughed it off. But over the next few years, he convinced our universities about IP agreements. I just the other day, I was telling somebody that IP is a nuisance, but you have to get intellectual property, wrap it up, get it licensed to have a startup. And so it was easy to do that because we had a lot of ideas that could be patented. And the universities at Maryland and Duke really bought into the idea. And there we were. We started off, and again, even to this day, that's 10 years ago, the industry in quantum computing, they're still doing a lot of research. And so it wasn't like we were building cars all of a sudden and we had to roll off 10,000 cars a week off the assembly line. We still had to execute a plan that we didn't know exactly how it would play out. We would need to invent new technologies. It would be very expensive. And that's why the business model made sense, because we could have budgets that were, we didn't have to worry so much about glue, duct tape and gluing things together with epoxy like we do in a physics lab.
How has NSF support impacted your work at IonQ?
I can give you one example. It's actually a little bit of a long-winded one. I was at the University of Michigan for many years, and they were well known for their work in pulsed lasers, high energy, ultra fast lasers to study fast dynamics and nonlinear optics and so forth. I had never used a pulsed laser in my life when I went to Michigan in 2000, and I got to working with some of my colleagues there, Phil Buxbaum, Gerard Moreau, and others who use these lasers. And I got less afraid of these lasers. Now, the reason I bring that up is that we had when the NSF Physics Frontier Center started, that was right when I arrived at Michigan. And we went after one of the Physics Frontier Centers, and we were awarded the Focus Center at Michigan that would study ultrafast science in many different facets. And I had not done anything ever in ultrafast, but I started to. And the reason this is important is that the laser that we used to control these atoms without looking, it turned out the best lasers were pulsed lasers. And the reason they were the best lasers is that they were made for lithography of silicon chips for a totally different reason, and they were very reliable. I used to say this laser has one knob and it's the on key. You turn it on and it works. It works for years. And that allowed us to not have to pay attention to tuning up a laser for 4 hours every single day, which I'd been used to, and we could move on to other things. And so in Michigan, I learned how to use lasers that were more mature, better engineered. And that was a direct result of a big NSF center there. And when I went to Maryland, we also had a physics frontier center on controlling quantum systems and so forth. And throughout the years, ever since I left NIST in 2000, I always had, I like to say that the NSF grants were the best color of money because I had more freedom. Of course, there are milestones. You have to write a proposal, and it's very competitive. But once the NSF awards you the grant, they're not going to check on you every 6 months and say, well, how'd you do? You promised you'd do that. You promised you'd do that. And there was, in a sense, trust. And that's what you have to do when you're on a path of fundamental physics or fundamental science that you're not sure where it's going to go. And of course, if you want to get funded again, you better show something, even if it pivots, even if it's something totally different, it's valuable. And those grants throughout the years, there were many programs in AMO and physics at the information frontier. NSFC really wanted to capture quantum in ways that the other agencies really couldn't. And they largely succeeded in that. And I will say in the last several years, one of my heroes at NSF, Bogdan Mihaila, he realized that we were not doing atomic physics anymore. We were not just doing atomic physics, but we were studying algorithms. We were designing algorithms to match with our atoms. And that, we call it a vertical research institute. It's basically applying quantum software to a very mature quantum system that we can engineer. And it's almost like a user facility, the way we run this place here at Duke, at the Duke Quantum Center. We have so many collaborations where people run their ideas through our machines. And it's almost like a company could do that, but we do it for science. We're not interested in optimizing a traveling salesman problem for Amazon. I mean, we'd love to do that, but we're also interested in studying phase transitions, simulating correlated matter. And again, I think NSF really, because of their science basis, it was a super important part of the U.S. posture in quantum.
What has been the biggest challenge translating research into more industrial applications?
IonQ by now is a very big company, and they're a public company. And with that comes severe challenges of talking to the street. You have to, I've never thought that job number one is to keep, to make sure the stock is buoyant, but I understand that it needs to be. Otherwise, the company doesn't exist. And so to me, the central challenge is how do you balance, it'll sound like a cliche, how do you balance future research and development with current revenue and sales and interest in the company? I'm not, I'll never claim to be a businessman or even though I'm involved with a company, but you have to have a little bit of both, and it really shouldn't be all of one and none of the other. You can't do 100% research at a company. People tend not to want to invest in that. If you have a long-term investor, it's probably not it's probably not the public that's investing. If you're only doing, sales and revenue, and you're not looking in the out years, that's an equal recipe for disaster in this field. So to me, that was the most difficult calculation, how much to sell, and how much to do R&D. I will add a short story on that. I was CEO of the company for about a year when we were just starting to produce our first few systems. And we started working with Amazon, AWS, Amazon Web Services, to put one of our machines on the cloud so people could, the great thing about any computer is that, especially a quantum computer, it doesn't need to be in front of you. You can use it on the cloud. And that exercise was tricky because it meant that we had to run a machine that would be up 24/7. And therefore it's not getting any better. It's just running. We're not improving things. And that's not what I'd been used to, always improving things, looking at the next thing. And I was actually sort of against doing it, putting it on the cloud. It would also get revenue, and that's fine. The revenue is good. But I learned later on that it actually was really important to build a system that would work 24/7. The engineering behind that, and engineering is something that I don't come natural to. It's very hard to teach engineering, systems engineering, but making something work 24/7 is an exercise that you will learn. The research systems will benefit from that. And that was an interesting lesson I learned. So maybe I err too much on the research side. I'm not sure, but we ended up putting them on the cloud, all of the clouds. And I think IonQ and other companies that do that are much better off.
Can you tell us a little bit about your experience making that jump from being a startup company into a public traded company?
We were sort of lucky in the timing of this. And it actually happened right out of COVID, when, as a private company, we had just raised a bunch of funding that would give us, I don't know, maybe a 3 or 4 year runway, as they say. Because we weren't really bringing in much money, we were spending it. And the investors understood this. This was a long-term play. And when COVID hit, our board, which was largely our investors, they said, well, we don't know how bad this COVID thing's going to be. You need to really think about that 3 or 4 years to be 7 or 8 years. Is that maybe there's a recession and so forth. And the one risk for the company back then was raising capital, really. We weren't too worried about our technical plan. It was very solid, not easy, but we weren't fundamentally worried about it. We were worried about having to raise money again. And that's the bane of startup companies with venture capital. You have to keep raising and you're always out there. When the opportunity came, a so-called blank check company, they also called SPAC, Special Purpose Acquisition Company, they wanted to make a play in quantum, knowing how risky it was, but they had a good foundation and an eye toward revenue and sales as well. Now, how you balance that, that's the tricky thing. But so that was the transition. And, we started getting more professional, getting a professional finance team, legal team, all that stuff that comes with a public company. The company was different after going public, for sure. And I think the pressure, their quarterly stock report earnings, where we talk directly to investors in the street. In terms of prosecution of our technical plan, that just went into hyperdrive. I mean, we were able to, with the public funding, we were really able to just go crazy and go much faster, make more systems, hire a lot of people. So I have to say, it was good timing. I think it's a little harder to do that now, but it worked out well.
For my last question, you said there's a lot of question for what quantum computing will ultimately be used for, but what impacts do you think it'll have on science and society?
Taking the long view, I'm quite sure that we will have quantum computers decades from now, for sure, that will be deployed for certain problems. And the tricky thing there is that the public largely doesn't know or understand or care about these new laws of physics. They really are fundamentally different laws of physics. And I think for people to fully appreciate the power of quantum computers and to accelerate their use in different fields, people should be learning the fundamentals of quantum, even at a young age. And I do believe, maybe it's more of a hope, but in 50 years, people will have an intuition for some of these weird things like spooky action at a distance, the Einstein quote about entanglement. They'll have a feel for it. They'll know that small, very simple systems, when they're cold and they're isolated, they behave according to these laws. So I think that's a total shift in the way we think about fundamental physics, for sure. And maybe it'll be infectious and hit other fields, from chemistry to more complex things like in biology. So I think quantum, it's not ready to tackle biological problems. They're still way too complicated, but eventually I am quite sure it will eventually. And I can say that safely because I probably won't be alive, when it hits that level. But I think, quantum is, in terms of the entire community of physics, we all, eat and breathe quantum physics, but it's not so useful out in the real world. This is a way to change that. And I think it also will propel physics overall as something that is absolutely required if you want to understand how to compute. I mean, I guess physics is behind the transistor. We all know that, but the model of a transistor is very easy. It's like turning on a valve, a water hose with a valve or something, electronically controlled valve. the models are, you can make models that go far. You don't have to learn all the physics. But quantum, unfortunately, it's not like that. We have nothing we can turn to. So I think quantum computing can be much bigger than just devices. It can really, I think it can really bring physics to the masses and get many more people studying physics and then going on to other things.
Special thanks to Christopher Monroe and Alexander Cronin. For the Discovery Files, I'm Nate Podker. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.